Have you ever really stopped to think about how our automated world, well, thinks? I'm talking about everything from giant factory arms to the traffic lights on your corner. There's a secret language working behind the scenes, a kind of script that turns electricity into action. Well, today, we're going to learn to speak that language. It's called ladder logic. So, take a look at this. This is the nerve center of a machine. And yeah, it's an intimidating mess of wires, switches, and relays. It honestly looks like total chaos. But inside this box, decisions are being made faster than you can blink. And that's the big question, right? How does all of that spaghetti monster of wires, become a smooth, reliable process? How do you tell this electrical beast what to do? You do it with this. This is a ladder diagram. It's the clean, organized, universal language of industrial automation. You can think of it as the Rosetta Stone that translates what we want into what the machine actually does. It takes that chaos and turns it into pure, repeatable control. Okay, so let's jump right in. Like any language, you have to start with the basics, the grammar. And in ladder logic, that means understanding the page it's written on, the rails and the rungs. It's called ladder logic because, well, it literally looks like a ladder. You've got two vertical rails, L1 and L2. These are the sides of the ladder, and they supply the power to the whole thing. Then you have the horizontal rungs, the steps. Each rung is one single instruction for the machine. And just like reading a book, power always flows from left to right, from rail L1 through the instruction on the rung over to rail L2. All right, so we've got our page. Now we need some words to write on it. The vocabulary of ladder logic is actually super simple, but it's incredibly powerful. It all boils down to just two main ideas: inputs and outputs. Think of it like a cause and effect sentence. The inputs, which we call contacts, are the if part. They're the triggers, someone pushing a button, a sensor detecting a box, you get the idea. The outputs, which we call coils, are the then part. They're the action. A motor kicks on, a light flashes, a valve opens up. If this happens, then that happens. Simple as that. Now, for our inputs, there are two flavors, and this is super important. First, you have the normally open contact. The best way to think about this is like a drawbridge that's always up. By default, it's open, so no power can get across. When you actuate it, like pressing a start button, the bridge comes down, the circuit closes, and boom, power can flow. And the exact opposite is a normally closed contact. This is like a gate that's always shut. Power is flowing through it all the time in its default state. When you actuate it, say by hitting a big red emergency stop button, you're yanking that gate open, which breaks the circuit and stops the flow of power instantly. And you've got to get this difference because it is absolutely fundamental. Seriously, misreading whether a contact is normally open or normally closed is probably the #1 reason for mistakes when people are trying to figure these systems out. One lets an action happen, the other is designed to stop it. So here's the key takeaway, the thing you have to remember. The word normally doesn't mean what usually happens. It means the physical state of that switch when it's just sitting on a shelf with no power, with nobody touching it. It's the device's default resting state. If you can lock that in, a huge piece of the puzzle just clicked into place for you. Okay, so we've got our words, our inputs and outputs. Now we can finally start forming sentences. This is where we combine those contacts to make decisions using two incredibly simple ideas: and or logic. First up, AND logic. When you put contacts one after another on this same rung in a series, you're creating an AND condition. It's like a chain. For power to get from one side to the other, the first contact and the second contact and so on must all be closed. If even one of them is open, the chain is broken and nothing happens. A perfect real-world example is a safety guard on a big machine. The logic says the safety guard has to be shut, closing its switch, and the operator has to press the start button. Only when both of those things are true at the same time will the motor actually run. It's a simple and, more importantly, a foolproof way to make sure nobody gets hurt. The other way to do it is with OR logic. This is when you put contacts on parallel branches, giving the electricity multiple paths it can take. With an OR condition, power can flow through this top path, or it can flow through this bottom path. You only need one of the paths to be complete for the output to turn on. Imagine a really long conveyor belt. You probably want start buttons at both ends, right? You want to be able to start it from station 1 or from station 2. By putting those two start buttons in parallel, either one of them can complete the circuit and get that motor running. It's all about giving you options. All right, this is where it all comes together. We're going to combine everything: our grammar, Our words, the ands, the ors, the normally opens, and the normally closed, to have a complete, useful conversation with a machine. We're going to build a standard start-stop motor circuit. Okay, let's build this thing rung by rung. First, we put in our stop button, and it's normally closed. That means power is flowing right through it, just waiting. Next in line is our normally open start button. Nothing's happening until we press it. The second we do, the path is complete, and our output, the motor coil, turns on. But here's the problem. The moment you let go of that start button, it springs back open, and the motor stops. That's not very useful. So here comes the clever part, the seal-in contact. We add another normally open contact, but this one is controlled by the motor itself. We place it in parallel with our start button. Now watch what happens. You press start, the motor turns on, and it instantly closes its own contact, creating a brand new path for the power to flow. So even after you let go of the button, the circuit is sealed in through this second path. This simple little OR logic is what turns a momentary press into a continuous action. It's a foundational trick, and it's what makes the whole thing work, right up until you hit that stop button and break the entire chain. And that right there, that simple circuit, illustrates the big secret. Remember that crazy, intimidating panel of wires from the beginning? It's not one giant, impossible-to-understand circuit. It's just a whole bunch of these simple, logical sentences stacked one on top of the other, each one controlling one specific little thing. You see, once you get that, everything changes. Each rung isn't just a line on a diagram. It's a conversation telling one part of the machine what to do. The whole ladder diagram, that's the entire script for the machine's performance. And learning to read it is like learning to read the machine's mind. It really comes down to this quote from the experts: master ladder diagrams, and you can read, draw, and troubleshoot any control circuit. This isn't just theory. It is the fundamental skill for anyone who wants to work in our automated world. Ladder logic was one of the very first real languages we taught our machines, and it's lasted because it's so simple and so robust. And it really makes you wonder, as we move into a future of AI and way more complex systems, what's the next great machine language going to look like, and what incredible things will we build with it?